I'm an OpenJDK developer. That's all you need to know. I do Java stuff, as you probably have seen as this title. So to start with, consider we have a simple web application on that. You probably all have these. Here in my example, it's a small documentation website that I have for like all the JFI events, for all the profiling events. And it's pretty cool, but consider now I have a DDoS attack. Someone malicious tries to like get the server down, and consider it's not just a simple application, but consider it's your application of your company. So what do? And what's the naive way to do? And that's why I got these flowers here. So the naive way is to do just cut this thing. And I pressed the wrong button. Interesting, it moved without me knowing. So, and then things happen. And hopefully, I found the correct button again. So that's the naive way, just cutting it as you saw here, and maybe terrible things happen. Maybe just the attacker is cut off, or you cut off, and they aren't receiving any packages. But there must be a better way than just carrying your appliance in the data center and cutting cables off. Because that's like not done in software, and we're here at the software conference. So the simple thing is what you could do, you could have a set of blocked IP addresses, and every time a package comes in to your, and every time a request comes in, for example, through your Spring Boot application, you just check, oh, is this IP address in the list of blocked ones? If not, then if it is, then block it. If not, then pass it through. And that's quite simple, and that's quite nice. Any idea, any of you see any problems with this approach? Anyone? Louder. Yeah, it's terribly so. It's even slower than going to the data center and cutting things. So the main issue is, consider now here we have our Linux network stack. So I'm looking here onto Linux because, if we're honest, all of our web applications running mostly on Linux stacks. So you have the package that comes through the network interface, then goes through the whole Linux network stack, and then it arrives up your application. That's pretty far above. So what you could instead do, you could use a firewall. For example, here to block an IP address, you could call IP tables and execute this command and block it. And that's pretty decent. That works. It's kind of programmatic, but that's couldn't we improve it? And if you see it here, it looks quite performant. That's like a benchmark done by the Cloudflare people. They drop packages, and what you see here on the y-axis, the amount of packages that are dropped. And with IP tables, you can drop like on their machine like 2 million packages per second, which is not that bad. But could get better? Of course, because we want to become a 10x firewall, and it's literally 10x. So you see here we can do things that are like almost 10 times faster, in this case like 8 times faster, approaching like the 12 million packages per second, which essentially saturates your Ethernet cable. And it's close to literally cutting the Ethernet cable when you drop all packages speed-wise. And that's pretty cool. The idea is that we take advantage of the Express Data Plane, that's the XDP, and this lies essentially between your network interface and your Linux network stack. So it's the first time the package enters your system from the Linux point of view, that's the place where we're checking these packages. It's pretty nice because consider when allocations occur. You have one allocation that happens when your package arrives from your network directly from your cable into your network interface, and then you have another one when it enters your proper Linux network stack and you attach things like IP addresses and other information that you attach as metadata. So you want to have as little allocations as possible because allocations just cost cycles. And if you use it there above at the application layer, you have a few allocations, and especially there it's even more expensive. But so when we cut it early, we essentially can block the packets at the speed of your network connection. And you can do it even faster with offload. And that's pretty cool. So there are currently approaches of implementing XCP, which is a way to programmatically modify your network interfaces directly in the network interface, directly in silicon, which is then even faster because the packet then never reaches your CPU if it's malicious. And that's cool. So there were traditionally two ways. There was the way of like, hey, change the kernel. That's a cool option because you can just like modify the network driver itself. But you would have to get a change past Linus Torvalds, and we all know that that's totally easy and it only takes like a couple of centuries for even single changes. No, but it's, I've seen it with other things that I tell you later, where people try to get things in, and it's cool. Linus Torvalds really cares about community, so he will probably not insert your change that you made in an afternoon into mainline Linux kernel. So you have the option of having a kernel module, which essentially allows you to hook into the kernel and modify kernel functionality, but that's also not great because it has problems with stability. To quote Craig Hartman, a kernel maintainer, you think you want a stable kernel interface, but you really do not. No, you don't even know it or why you won't. And he quoted things about, for example, the USB interface, where USB interface with every USB iteration it changed, so it wasn't stable, but what the kernel really cares about is performance. You want to have the most performant, the most stable interface, the most stable operating system, and you don't really care about stability that much in this regard regarding APIs. That's a problem, so essentially the two ways are off if you aren't like a company like Meta or Google, and even they find it quite difficult to do this because it costs a lot of time and it can fundamentally crash your kernel, and that's not a great thing in production. So can we do better? Yes. And there's where the beast comes in. It's eBPF. It's really cool. To quote a guy who is most famous on the internet for shouting at hard drives, Brendan Craig, eBPF is a crazy technology. It's like putting JavaScript into a Linux kernel. And he normally looks like this if he isn't shouting. And if you want to know more, I'll link the YouTube link there. He essentially wanted to show his monitoring tools for disks. Anyway, the idea is that eBPF is making the kernel programmable at native execution speed. So what this means is you can hook into a kernel at certain places and like hook it in, like when some of you might know Java, so when you have Java UI frameworks and every time you press a button you can register a handler and then this handler can modify some behavior. That's the same thing here, but only in a way cooler. So the idea is with eBPF, we have our eBPF program. We typically write it in C or Rust. And this is then compiled down to a bytecode. It's not too different from like a basic JVM bytecode as such. And so it's compiled down, and this is all happening in user land. And what you have in the Linux world, you have a user land and a kernel land. So user land are like the applications that you normally write, like unprivileged things, and in kernel land, that's like running directly in the kernel. And we can use a system call to communicate with both, between both. So it's essentially an API of your kernel. And so you tell the kernel, hey, please load me this program in. And then you have a verifier, which is pretty cool, because when your eBPF program has, for example, misaligned memory access, or it doesn't check whether a pointer is null and access it, then you can potentially crash your kernel. We don't want to do this because we can't really recover from this. So we have a verifier that checks for out-of-bounds things, for misaccesses of pointers and other things, and it can do it because it limits the amount of code that you can, the amount of steps that you can execute in eBPF. That means essentially that it's a restricted execution, but it's good enough. We can write simple loops, and that's good enough for most applications. Just keep this in mind, and making the verifier happy is the same like with Rust. Making the borrow checker happy can take some time. But then when you have a program that's approved, that's cool, then it's usually JIT compiled. So the JIT compilers for this bytecode on all the common platforms like x86 and 390. You can even run it on your mainframes at home. But then you attach it, and we saw before that you can attach it directly in the network interface via XTP, but you can also attach it at various other places. And that's pretty cool, and then because then you can also communicate via system calls with your application. And what it offers us safety and security because we have a verifier, so we check it before, and it offers us also continuous delivery because we don't have to restart the kernel, rebuild it and everything when we modify, for example, our network stack. It gives the efficiency because it's almost close to native execution speed because of the just-in-time compiler and how this was developed. It essentially gives us, it essentially came out of the movement of this computation as software, which we have with Docker, and then people thought, hey, can we have network defined software? And that's what it essentially is. It allows us to modify things in software that were previously not possible. And the cool thing is, it's a standard. Yes, it changes, but it's standardized enough that you can run applications on multiple kernels when you compile them for one, and that's pretty decent. So, of course, you might wonder, how can we then share data? You saw we can attach it in the kernel, and they'd like to show you examples of how to properly do it in demos. So how can we share data? An idea would be in normal applications to use sockets or to use shared memory. The only problem is we're communicating between kernel space and user space, so we want to have more checks on it. And so what we can do, we can use eBPF maps. eBPF maps don't have to be maps. It's more like the PHP terminology of map, where everything is essentially a map. But here, essentially, map describes a commonly used data structure that's shared, and you have loads of different maps, but the map types, but the idea is essentially you have your eBPF program that communicates with these maps, sets values and such, and then your user land program can come in and also access them, which makes it pretty nice because you can, for example, log values out. And yeah, that's how it works, and it's really the cornerstone here. There are lots of types because the kernel developer thought, yeah, we probably usually need more than just a hash map, so there are hash maps with that remove the least recently used element if they get full, which is pretty useful for caching. And I wish that Java would have these by default. We have arrays, we have ring buffers, and all this makes it fairly easy to develop this. And if I'm honest, it's far easier to develop than like the normal C programs. Because in C, when I start out, I have to get a library for getting simple hash maps. I implement them myself, so it's pretty nice. So as I said, you can hook everything. You can attach small programs to modify behavior at almost every place in the kernel, which is pretty decent. They even approach us to do this with userland programs, but it's still an early field. You can attach it at so many places that I only myself explore like a percentage of so. And I show you later at the end that we can do even more crazier things. Where it's commonly used, besides like doing firewalling, like Cloudflare uses it for their firewalls, Meta uses it also for their load balancing, but you can also use it for observability and monitoring. Many people in the OpenTelemetry space use it because you have application-wide knowledge. So the idea is that you're on the kernel level, so you see every application and you can do profiling across multiple languages, which is pretty cool, and can have access to things like network information that you would never have access to because you're really logging the packages at the source when they're coming first in. It's also cool for security control. If you ever heard of AppArmor, that can also be used with eBPF. And what's also pretty cool, you saw this before, this like CrowdStrike. It was really nice when everything ground to a halt, just because you had like these every out of bounds reads. So that could never happen with the verifier, which is cool because the verifier checks and is like, nope, I can verify that you can access this array value, so that's cool. And that prevents a lot of things here. And that's probably also one of the reasons why Microsoft more and more pushes eBPF into their own kernel. And they even now released the eBPF for Windows. But of course, eBPF has bugs too. All my applications have bugs all the time, yours probably too, so why should eBPF differ? But most of the bugs are in the verifier, so please, please, please don't run eBPF programs from untrusted users. And even if you run them from trusted users, know why you execute them then, not blindly execute them. Because they have kernel-level access, they can access all the memories, they can access all the passwords, everything stored in, so yeah, please don't install malware on your systems. It would be nice, would make life a little bit easier. And the interesting thing is that with eBPF, because you can modify kernel-level applications, you can also pretty much hide your eBPF attacking applications from the view of normal systems that aren't like running in kernel, and that makes it pretty hard to detect them. But anyway, the eBPF ecosystem is quite large. It grew when eBPF started in 2016. It was just a couple of forks between a couple of companies, Netflix, Google, and Meta, working on it. But nowadays it grows and grows and grows, and adds even more applications. And as you see, the ecosystem consists of like the Linux kernel and like the Windows kernel. And then you have on user space some libraries, that some SDKs that work with that, and then on top you have eBPF projects that facilitate the use cases. And there's even a children's book if you like to read something with your child. But anything missing here in the user space? Yes? Yeah, there's no Java. That's not good, because I like Java. I'm an OpenJDK developer. Why can't I use Java here? And that's essentially what I thought when last year I thought, hey, what could I contribute to the eBPF ecosystem? I'm like, maybe add a little Duke there. And if you wonder why I'm in this t-shirt, because I was last week in Vienna at the Linux Plumber conference and talked about the very same topic, be like, have more Java in the kernel. To quote Brendan Craig again, eBPF is a crazy technology. It's like putting Java into the Linux kernel. And once I was introduced at a conference being someone who worked on JavaScript. This is my redemption. Anyway, and for those of you who know the Java Zone conference, I want to use a programming language which doesn't only run in user land. So here you go. That's the project called Hello eBPF. It's humbly known as Hello eBPF. Hello eBPF, Hello Java. You find the link of all the resources later in the QR code. But of course, it's work of progress. It's a side project for me. I'm happy that I can work on it, but still, it's a prototype. But anyway, I'll show you in the following how you can use eBPF, at least like in demo applications. So now we're going to the live coding, or how I'll call it, having fun with eBPF, and let's see where the demo gods like me. But first, a short demo, so I can show you what you can actually do with eBPF. This is the title-giving demo. I finished this demo 3 months after submitting this talk here. So let's see whether it works. Essentially, the idea is this is an application written in JavaScript on the front end, but Spring Boot on the back end. And the cool thing is, when you develop all this in Java, as I show you in a minute, you can easily connect it to Spring Boot without that much fanfare, without calling other applications via shell commands or anything, or even writing Python at Go. This. What we can do, we can just send some JSON in there. The idea is here that we say, oh, please block every IP address from port 443, from source port 443. That's essentially the HTTPS port. So let's see. Oh my God. And I need to give it some power, sorry. And essentially we can do this. Sorry for that. Essentially, yeah, we added a new firewall rule. Now we can trigger a request to google.com. I always use google.com because I assume they are online all the time, so we can request it. And we see here it's blocked. And that's running in the kernel. So you have code running in the kernel that blocks all these packages. And we can reset the rules. And now it stops. Yay, and that's all for my talk today? No. We're doing some live coding. Of course we do. So first, so that you trust me that I can write Spring code, don't do it. I use ChatGPT for it. It's the best way and the only way to write Java applications. No, I'm just kidding. Essentially, the idea is here that when we add a firewall rule, it's serialized by the browser into a JSON. You saw a JSON here, and then it's deserialized automatically by Spring Boot. And what we can do here, we add the rule directly in the kernel. So that's essentially all the code to put firewalls rules in the kernel. And I'll show you now how we can develop our own applications in the next following 20 minutes or so. So let's see. Live demos are always interesting. So what we have to do is we have to first, because it's like a more complicated thing that I'm doing here, so we have to first give it a license, because it's important to know that in the kernel, when you're doing eBPF, there are methods that you can use with like an MIT license, but many of them are not with a license exception. So many of the methods you use, for example, when you do some more sophisticated things, you have to declare that your program is GPL. And that's what I'm doing here. And then what we want to do is we extend our BPF program. That essentially means that we tell my code later what we want, that it's an eBPF program, and then we want to, here in our example, we want to do some system call hooks because it's easy. We want to hook, for example, the open-add system call, and open-add, let's look for it. And that's just an interface that we implemented, open-add, no? To look for it here. Every time we enter open-add, we call this here, and we can call trace print k, and every time we access a file with the system call, we call hello world, and to make it easier to see that it's really changing, we add a file name here. But now we have to tell our system how to load it and how to compile and everything. And then so in common Java fashion, we have a main method. What we essentially then do, we load our program first. So we use bpf program.load, so that loads because I'm doing magic behind the scenes that I show you in a minute how it works, but essentially when you compile a Java application, this part of the code here is compiled to C code, and then compiled to eBPF bytecode, and then when you call load, you load this in the kernel. So this code here runs in the kernel. This code here doesn't run in the kernel. So I have here a limited way of Java that I can express, but here I can do every Java. I can, for example, write a Spring Boot application if I want, and then I attach it, and that should work. So I hope it works. The only problem is the Java ecosystem is not the fastest ecosystem to compile, and essentially when you're adding some magic, it's not getting better, but let's see. And the cool thing with this is you can write your applications eBPF code in the same Java, in the same class that you also write your application code. So you don't have that many problems with code duplication. And you can even have code, because the amount of Java that you can write is limited, but you can even write code that can be run in both. So let's see, run demo.sample. So you see here, that's like, every file that's currently accessed in your system. And that's just a couple of lines of Java code and implementing the interface system call hooks. And yeah, we can do many things with it. On more interesting example, because when we're relating to firewalls and to other things, is that we can simply write a program that drops every third incoming package. This could be used for example, for monkey testing, so for case testing. So it's essentially a monkey that every third package is like nah. And you can even do like pseudo random number generators or something. So you can do interesting stuff. So what we first do, we define a global variable called count, as you see here, and then we have a method. We annotate it as BPF function. The function here, the XCP handle packet method, is implicitly annotated with this. So should drop, what does it do? It just checks, oh, should get, is it model 3, is it 1? If so, return true. And so what we have with handle packet, that's from the interface XCP hook, and the idea is essentially that it gets a pointer to an XCP struct. You have to see that essentially what we're doing in Java, we're modeling C, but it still type checks, so you're kind of writing a mixture between Java and C, and that's part of the magic. So we first increment the count, and then if we should drop, we return the enum value XCP drop. If we shouldn't, we pass it. And now we just attach it here. And the cool thing is we can access the count variable the same way as we access it here in the eBPF program. And now we can probably try it. It is compiled the last time, so I don't have to recompile it this time. XCP drop every third package. So what you might have noticed is that this is a Mac that doesn't run Linux, just because having Linux systems on stage on presentation is slightly riskier. So this runs a VM. So essentially when I'm pressing enter, I'm creating new messages that are passed into the VM. But anyway, you see here, it logs, and it's pretty decent. You can do it for simple monitoring tasks, and you can even build like your own Wireshark clone with it, which I found pretty nice. But how does it work under the hood? So how it works is that I told you before that when a network packet comes from the internet, your network driver essentially asks the eBPF program, hey, your XCP hook attached program, hey, what should I do with this packet? It can then decide whether it should pass or not, and then it gets passed further up in the Linux network stack and then to your application. And the cool thing is your application will never know that there's like an XCP hook running in kernel doing this. So it only sees that every third package is dropping, but that might be due to a flaky connection. And then your eBPF program, as we see, can communicate statistics up to the eBPF application. But of course, we can also use maps, as I told you before, to pass, for example, blocked IP addresses down. And how this then, and the interesting part here is that we're getting at XCP level, the package, like the proper packets, just a few bytes, and we have to parse it ourselves. So I was at university like too many years ago, and we learned this, and I had to re-look at my old material, how networking works, because usually when you're developing applications, you never consider, oh, where's this byte? And an interesting part is also the network byte order and your host system byte order is different, and that leads to quite interesting bugs when you don't consider it, because one is big endian and one is lower endian. And yes, I spent afternoons on this before I found it. Anyway, what you saw here is that I'm essentially trying to run Java in the Linux kernel, to quote Clark's second law. The only way of discovering the limits of the possible is to venture a little past them into the impossible. And this all was made possible by Project Panama that came in JK22, so quite recently, which allows us to invoke C method quite easily, because what I'm essentially doing, I'm building a sophisticated wrapper around libePF, which offers me basic functionality like load something into the kernel. And so how this works, when we reconsider this application here, our method should drop. We take this, it looks like Java, it works like Java, but you also see that we need to support unsigned integers, so there's an unsigned annotation there. Then we take it to an annotation processor that essentially takes all the data structures, and you can define structs and units and such, and converts them to C code. And then we have a Java compile plugin that takes the abstract syntax tree, analyzes it, and then emits eBPF bytecode. And so what it essentially does, it converts the Java code that you see here to the equivalent, well, equivalent is a hard word, but to something that looks similar to the C code. And that's pretty cool. That allows you to write kernel code inside your application. And for all the compile nerds out there, I hope there are a few. Essentially what it then does, it uses Clang to compile it down to eBPF bytecode, which is pretty simple. But let's do more fun stuff. We still have 17 minutes, so let's have some fun. So what you might have thought about is whether we could use our sample for something nefarious. Any ideas what we could do when we get here a pointer to the file name in? Anything? Yes, we can, and that's pretty simple. So what we can do if you're nefarious, we can forbid the user to access a file. This here is a simple function that's also compiled to C code as before, that just checks is this file that's coming in the /tmp/forbidden file. And what we in enter open then just do is like we have to copy the file name in, because you have to keep in mind that file names comes from the user because it's a system call, it comes from userland, so we have to first read it because we can't otherwise access it. BPF traceprint K is interesting, it knows how to do this, that's also kind of magic. But the idea is here, when this file is forbidden, then we write back to the user, for example, the empty file, and write back to the file name the empty file, and then because it's the enter open add system call, what this means is that the system call that's like further processed by Linux kernel is like, I don't know this empty file. What do you want, user? And then just returns an error. And that's pretty cool, because we can essentially forbid the user to access this file using this file name. And let's try it out. And I'm starting another shell. The important thing is here that it of course has problems. For example, when the user uses a symbolic link, it doesn't work anymore because then the file name is different. But we can now do it, and for example, we can touch it, touch tmp/forbidden. Typo. And so it touches like, what do you want with like the empty file? And it's also locked here. Access to file is forbidden, as we saw here. And that's pretty cool because we can write simple applications to test and also do some logging. And of course, there are other ways to do bad BPF. Someone even gave a talk about it, but you can see that it's a pretty cool tool. And what's also nice is you can do more stuff. For example, you can, with Hello eBPF, you can define structs in Java code that you can both use in Java code and in C code. For example, you can define when we log all the open ends, which file was accessed by which process, we can here define an entry, and that is a class with a string, com, and an int count, and then count per process how many, I think it's per process how many files were read, and then we have here maps that we can easily define and access both in Java land and in user land. For example, you see here, we access the map. What we do here, we read from this map and then increment. And also in Java land, what we do, we can just use for each over it and access it directly. And do many more crazy things, and also implement firewalls, which other people done, and I tried my very share on it. But now, of course, if you want to know more, I write a blog post every other week since January, so there are now 15 in, and you can look forward to having some demos also coming on the blog. And now glimpse in the future in like the last 10 minutes. What my aim is with this project is to make eBPF accessible for like more than just your standard C developer, but for people like you that like might wonder how this works and might want to like dabble a little bit in it, because many people know Java. And so it's really accessible. I hope that Java will just also be a part of the ecosystem, because it's, after all, one of the languages that are used for server development. And of course, what like if you go back from like the Java side and go more into the broader eBPF sense, into broader eBPF world, it gets us a little bit closer to microkernels. So we're getting more and more functionality out of kernel modules and out of the kernel into applications that are essentially written by a user and then inserted at runtime. That makes things so much easier, but of course it makes also debugging harder. And recently it's also quite interesting when you, for example, on distribution vendor like Fedora or such, and now you have code that's running in the kernel at your customer that you can't control, so it will probably also make quite a mess. And I don't want to be the support person that needs to help the clients be like, oh, my application doesn't work, my kernel is broken. Yes, you installed this random eBPF code from somewhere on the internet. Let's see how that works. I saw it worked really well in the JavaScript world anyway. What you can also do, we can reimagine kernel fixes, because we can modify the behavior at kernel level. And so, for example, when we know, okay, this access to a system call, this can break potentially our system, we found an issue, then we can write a small eBPF program, hook in and check for these arguments and just disable them. And that's far easier because we can distribute it. So with eBPF, you can do things that previously were like, oh, I have to recompile the Linux kernel and then ship it to our 10 servers to test it out. It's like, oh, a flick of a finger. You saw it, how fast it is. Even when you bring Java in the game, it's just a matter of seconds. And a thing that I pretty much like, and I'm now part of just as a hobby because I like the people there, is GetX. So the idea is that you can write your own Linux scheduler. And yeah, you might wonder, can we write our own Linux scheduler in Java? Oh, am I the only one who wonders this? Okay, I'm the only one. I'm not wondering anymore. I wrote this last week, and I gave a talk on it at the eBPF Summit online. So essentially the idea is that with a prototype of my Hello eBPF library, you can just implement the interface scheduler and implement a few methods, essentially 4, and then 25 lines of Java code later, and I mean like the whole Java file is just 25 lines of code. You have a scheduler that works, that runs. When I gave the presentation and I had a Linux machine, this even ran on the machine that I was doing the presentation with, so that's cool. And that's pretty cool because you can use this, for example, to reimagine testing for concurrency stuff, and that's a thing that I'll be working in the following week, so you can follow up. And to do proper concurrency testing where we can control the scheduling order. And that's the cool thing with eBPF, we as the user, we can control things that previously were only controllable by people that worked like for years in the C code mines of the Linux underbelly. And that's essentially what's coming. So for example, with Linux scheduler, to work on the Linux scheduler, before SCADX, you had to have so many years of experience to even start to even be able to get something into the kernel. Now you just implement the scheduler interface in Java and be done. And that's pretty cool. So yeah, my final thoughts is that it's a cool environment to work on because the ecosystem is so young. You can even like as a humble OpenJDK developer, you can still make a splash in the ecosystem because it's not that large. So you can just join and have fun and yeah, come to conferences and also have fun. Anyway, if you want to know more, I collected all my eBPF resources at this link here. There you can also find links to my blog. I want to say thanks to Dylan who helped me with all my eBPF versions, even at random days of the week, as you do. I want to thank my team here. I work at Submachine. We're like the third biggest contributor to the OpenJDK and one of the open source projects at SAP. And you find me on Twitter and on Mastodon. That was my talk. Thank you.
Questions? I'm not asking you why you write a firewall in Java.
Well, if I'm honest, that was like the first things that people asked me at Linux Plumbers, and I'm like, because I can. Why not? Yes. Anyway.
If you can, have you thought about implementing SE Linux in eBPF?
So that's what people essentially did. So AppArmor is, I think, part of SE Linux. So yes, people are working on it, not me, and they don't want to have these things implemented in Java, I think. But yeah, of course, there are people working on SE Linux related stuff, and there's also, it's under the project of Linux security modules, LSM. You can find quite a lot of information, and that's where like most of the effort is going in the security space.
You mean using eBPF?
Yeah, they're using eBPF. You can essentially what you can do. I couldn't get it running on my machine, but let's see. You have LSM hooks, and you can essentially have methods like restrict file open, and if you want to have a peek under the hood, you have the method. You have like the method restrict file open, and that's what it looks like in C behind the scenes. And this is, for example, used to restrict the file access properly, not like we did it here in this example where you can just set a symbolic link. So people are working on that. People far smarter than me, hopefully.
Hi, thank you for the talk. This may be a stupid question, but do you see this as an interesting technology or interface for regular application developers, like working on plain old business backend project,
yes,
or more something for people that happen to be working for, I don't know, Grafana?
No, so especially with the testing angle, and that's the angle that I want to continue working on the side in the next couple of months, is that when you consider, for example, you control the scheduler, you can quite easily test for execution orders. So what you have in your applications, especially when you have multi-threading, you assume, oh, this thread runs and this thread runs, but you never, when you have a unit test, you never can test, oh, this thread runs on a different CPU than this thread, and they run concurrently, and now I'm testing this very scenario. That's especially important when you want to test how your system behaves on the simulated load, because you can, for example, push these two threads onto the same CPU, see what happens. See what happens if like half of your threads are randomly stopped for 30 seconds. Does anything crash? So I think that's essentially, especially when what I want to do is add an interface layer on top where you just have a Java API and you use this. So I think as a normal application developer, you probably will be in the future using tools based on this. And you can try it out. It's not that hard. It only costs you a couple of months.
Thank you.